Enter the room. While I'm getting ready to use my hammer to put nails in the wood, only people being yesterday during James' talk are getting the message. All right. So we're going to change. We're going to go from design to something a little bit different in the checkbox list. I don't remember how we got in touch with each other, but I probably just saw an amazing talk of yours somewhere, and then we were chatting. And actually, I saw you when I was in San Jose, but we didn't get time to speak with each other. So I'm really happy that TJ is with us today, all the way from San Francisco, right? On Atlanta, yeah. I'm messing up with Atlanta and San Francisco. I'm gonna be in trouble with both of you guys. And from Atlanta, and so give him a warm round of applause for TJ. And I need to swap this.
Hello, everyone. So this is going to be slightly different, only a little bit. I will preface all of this by saying that I basically am a researcher, sort of. I find things that are sort of interesting to me, and I try to pursue them to their logical end, or as far as I can, or as far as the compiler allows me. And then I talk about them. So today we're going to talk about basically trying to translate a bunch of mathematical concepts and bring those into testing, right? And see what we can do and why we might want to do it and things like that. So just first of all, I'm going to talk about my motivation. I've started a little bit with just the research thing, but I am most concerned with modeling. Yes, this kind of modeling, but also trying to put concepts into code. I am more interested in modeling things, abstract things like points or notes or music theory or, these things that you don't necessarily say, oh, I'm going to, have a RESTful service and I need to model the data that's coming down and show it on the screen somehow. Because that modeling isn't that interesting, really. You're just saying, well, I get some information, this is the structure that it's in, I put it on the screen. But trying to say, can I model all of the information that we have about trees, like trees that grow in the ground? Can we do that? What does that look like? And it turns out that when you start to do that, you want some generalizations that you can make about the shape of information and what happens when you put them together and pull them apart and operations that you can do on them. Also, one of my motivations is just maths in general. I like math and I want to learn it more. In university, I didn't have to do any math. And after that, I realized that was a mistake, that I didn't do any math there. I really like it. And so I'm just trying to make up for lost time. Right, I'm trying to cram as much math education as I can get in, and the common theme here is just self-edification. And I say this to really emphasize that I understand that a lot of this isn't terribly practical immediately. Right, I'll finish this talk, and you might go, "Yeah, but when am I going to use that in my code?" You might not. Hopefully, you will. Hopefully you'll think it's really interesting and you'll say, I have a couple models that would really benefit from this. But if you don't, hopefully it's just kicking around in your head. This thought is here and it's something that has been added, right? Basically, this whole project can be summarized by Jeff Goldblum. I was so preoccupied with whether or not I could do this thing that I really never stopped to think about whether or not I should. All right. So, like I said, I like to model like musical intervals, but if you were modeling something like inventory, right, you might think about how two pallets or two shipments can be added together, right? Adding is the operation, the two shipments are, two objects in your set or in, that you're talking about. And then you have characteristics of those things, right? So if someone has two different orders that they put together, that's just like, sort of normal addition. And you can say, well, nothing should be lost when you add these two things together, right? And if you say someone has the same order and they multiply it, they say, I want 5 of that same order, right? Multiplication becomes a thing, and it works just like multiplication that we think about with arithmetic. And the properties that multiplication has, right, translate into our model. Collections are actually probably one of the nicest things to think about in terms of maintaining associativity and commutativity. We just don't implement array or set very often because we have them for free. But if you think about a set works just like a mathematical set, right? And all of the properties that you would have where you say, oh, well, like if I subtract some things from this set, it works just like a mathematical set, which is why I'm going to use that as an example later, because it's easy. Colors, light-based colors, work in terms of addition, I think, pretty well, right? When you add two colors, there's a lot of properties that get maintained and things like that. So before we get into really, really the heart of this talk, I'm going to have to give you a primer on SwiftCheck. Right? So SwiftCheck is a tool for property-based testing. It's modeled after QuickCheck, which is from Haskell and Erlang. And the basic ideas I'm going to go over. And so how do we find test cases in SwiftCheck? We introduce randomness into our system so that we can say, all right, well, I have this kind of thing, and I'm going to say for any arbitrary instance of this thing, right? So if I'm talking about arrays, I'm going to make random arrays, right? And then I can't have it be completely random, because once I find a problem, I want to be able to say this array had a problem. So I need to be able to reproduce that randomness. And then once that fails, I need to be able to try to shrink it, because if I made an array with 10,000 items and I say that failed, well, fine, but I don't know why it failed. Did it fail just because it had 10,000 things in it? Or was the last thing a problem? Was the first thing a problem? So we'll talk a little bit more about that in a second, right? So let's say that we have a type, rational. It's a ratio, it's a fraction. There are many words for this thing, but that's what's being modeled here. We have a numerator, we have a denominator. Top number, bottom number. With me so far? Some nodding? Yeah? Well, I want to be able to talk about the properties that ratios have. Right? I want to be able to say ratios are commutative when we add them, or associative, or this or that. So how do I do that? Well, first, I want to be able to make random intervals. Completely random intervals. Well, completely random intervals. Computers and such being what they are. So there is a protocol, arbitrary, and it only requires one method, which is make me a random thing, whatever I am. We're going to use generators, so arbitrary instances for integers or strings or the primitive types that we have, so that I don't have to think about how to randomly generate every aspect of this. And the thing that I'm going to return is going to generally be a generator of A. Right? It's going to be something that just makes random A's. So to do this, we're going to use the compose method on gen, and it's actually pretty neat how it's put together. Basically, by overloading and some generics math or fanciness there, we can just say, hey, I need 2 integers. I know that there is an arbitrary instance for integers. So in the 2 places that I would actually hand in integers, I'm going to call integer arbitrary. And make 2 random numbers, hand those into my constructor, and end up with a random ratio. But can anyone see a problem with this?
It's very big.
It can get big, but that's fine. That's fine. We'll figure that out in a second. Zero, right? Zero can be a problem because dividing by zero is not great, right? So this is our generate, except this is wrong. Sometimes I will get zero in the denominator. So I need to filter just a little bit. I need to say, well, sometimes for the denominator, I should use this, in fact. Right? So what we end up with is actually this slide, where we say the numerator can be whatever we want, whatever it ends up being, but the denominator can never be zero. And that'll give us a random number, but it will reject zero in the denominator, and we're good. And now I get a random ratio, but yes, sometimes the denominator or the numerator will be enormous, but we'll try to address that later. All right, so now that we have this way of making random ratios, what do we want to test about ratios and rationals? Oh, well, I cut some stuff out, but one thing that we might want to test is that if we get the inverse of a ratio and then inverse it again, we get the same ratio, right? You don't test just that, but that is a property of ratios that should hold, right? If we flip it twice, we should end up with the same number. If we have some property that will give us the complementary ratio, the thing that we can add to the ratio to get 1 or 0 or whatever, there are certain properties that we can establish with that. So we're going to look more at that in a moment, but now let's talk about modeling, say, sets, like I said. Right? We have this idea of a set, and we have 3 sets here. Sharon, Lois, Bram is in set A. Zach, Tom, Tim, and Brad are in set B. Tim, Tom, Mr. Lord, Mr. Chuck, Brad, and Be Real are in the last column. Just so that you're not puzzling this out, Sharon, Lois, and Bram is, well, Sharon, Lois, and Bram, that's the name of their band. And we have, Rage Against the Machine, and then we have Prophets of Rage, right? But with these 3 sets, we can actually talk about some set math. We can say, let's make the band Sharon, Lois, and Bram, and Zach, Tom, Tim, and Brad, right? We can say, what is A plus B? We can say, what are the band members in Prophets of Rage who were not in Rage Against the Machine? We can say C minus B, right? Right now, what I care about most is addition, just addition. So in the structures that I'm going to be talking about, I'm going to usually pick one operation or maybe 2 to talk about. And what we're going to do is we're going to say, given a set of items and this operation, what can we say about this for everything? So there are some words, magma, and it's not the molten lava stuff, right? This is just an algebraic structure. I don't exactly know why this term was chosen. And a magma with one more requirement is a semigroup. And a semigroup with one more requirement is a monoid. We don't care about what those requirements are right now, but when I say hold the lattice, this structure and this relation, how it's like, oh, and one more, oh, and one more, and you make this web of items, that's what I'm talking about when I say hold the lattice. Right? Let's talk about what a magma is. Right? Well, a magma is just a set and a closed binary operation. That's all there is to it. Simple, really. Okay. So let's take a second. Closed. What do I mean by closed? A closed operation is something that takes one item of the same type, or 2 items of the same type, or 3 or n items of the same type, and returns an item of the same type. It's closed in the type that it works with. So it's not A and B equals an A, or A and A to a B. It's all A's, just like turtles, all the way down. Okay. I don't know if that joke translates to German, does it? Anyway, so that's a closed operation. Hopefully, via programming, we know what binary means, right? It takes two items. So a closed binary operation is something that goes from a pair of A's to an A. Yeah? All right. Now that we know what a closed binary operation is, we're going to start to try to model this in Swift, right? I've gone pretty long without showing you any Swift. Well, actually, I guess SwiftCheck. So I make this protocol called a transform. And the reason that I start this high up is that I might not only care about binary operations. I might not only care about closed operations. So I'm leaving myself some wiggle room. And all I care about is that the operand, the item, is equatable and arbitrary. That's it. Now I make a closed binary thing, and it extends transform or inherits from transform. And now we're going to talk about a function. We're going to say operand and get. Okay, so this is the actual function in Swift that we're talking about. And you can initialize this with that type. And I realize now, naming-wise, I might have to say left operand or first operand or something like that, because I might have more, just like I said. And this is closed binary because it takes two of operand and returns operand. Now, all of those things were abstract. Those were just protocols. I can't hand them around for various reasons. So I need to make a concrete, like a struct or a class or something that I can actually make an instance of and hand to someone. And that's all this is. So this looks more complicated, but really it's just me making an actual instance. All right. We're almost at the payoff. Almost. So I've mentioned that we have associativity. How many people remember the idea of associativity? I don't even know if that's the word that is used here, but hopefully it is, right? Commutativity, identity. These are all sort of mathematical things that you can talk about, right? And I, like I said, think that it's interesting to be able to say that this operation over musical intervals, which is the thing that I cared about initially, is associative or it's commutative, right? And if this holds, then I can just keep that idea in my head as I'm working with them and say, yeah, when I do this operation, I shouldn't have to worry about the order that I put these two things in. Or I do have to worry about the order that I put these two things in. Something like that. Now, just making an enum and naming it this, turns out, does not prove anything. Right? You actually have to find some way to establish that this is true. So for each of those items, I have a concretize sort of thing. And every time you add a new property, you actually have to think of how would I make a SwiftCheck property that would capture this property. So for associativity, I say, well, given, we don't have a pointer here. Given two operands, right, just an I and a J, whatever operation it is, ij, should be the exact same as ji. And that's all I'm saying, right? This is a lot of text for really, this is the heat. This is what I care about. Everything else is so that my testing machinery actually does what I want it to do. Right? When this fails, I'll print off this little bit of text and stuff like that. So we have to make it concrete. Like, this is the actual code that you will run to prove that this is true. So let's get back to the definition of magma, a set and a closed binary operation. We can kind of prove this now. Like, we have some idea of what code we need to write to prove this. Now, again, this looks like a whole bunch of code, but op type is just type alias for operation. Operation is just an operation. And then I accept an operation. This is all we care about. This is confusing at first, but I'm working over a set. What is the set that I'm working over? My operand. So if I'm thinking about plus over integers, integer is the set, all integers. So just by virtue of having a type that I'm working over, I've covered that. I have a set, int. And by having a closed binary operation, I've covered that. There are no other things to worry about. So I don't have to prove anything else to prove that I am a magma. Done. And you might say, TJ, why did we do any of the other things then? Well, let's move on to semigroup, right? Right, semigroup, what's the definition of semigroup? A magma that is also associative. And hopefully you can guess how we might write that. This looks very familiar, but it adds associativity right here. And you saw earlier how we had the concretize associativity and the I and the J and the J and the I. And what that means is when I go to run my tests, we're going to concretize the property. And then SwiftCheck is going to run that 100 times with random input. And if one of them fails, well, I think you're not associative because I found something that failed. But if all of them pass, we're good. No problem. Done. Okay. I was going to open up Xcode and do all that stuff, but let's not tempt the demo gods today, right? All right. So why do any of this, right? It seems like I sort of did all, put all this scaffolding up to do a parlor trick. Really, again, research. I'll talk about the things that I figured out and found out in making this and talking about this with a few other people. But overall, I feel like there are some cases when we get into modeling abstract things where this is helpful. It's helpful to be able to say that no matter what two I put together or what order I put them together in, it should be the same. Or it can't be the same, and the order really matters, right? How many times have you had a method where you accidentally called the method on object A and then passed in B when you meant to do the reverse? And it'd be nice to have somewhere where you document, like, you shouldn't do that. That actually matters. It does matter what order you hand these two things in, right? I'll use it because I do, right? I'm going to open source this and make it available. It's not that interesting right now because it's I need more properties, but I already use it for my music theory library for various things that I just do for fun, right? But now we get to the sad truth, which is some of these properties are actually lies, just lies. So integer, for instance, I would like to prove that integer forms a ring, which is another algebraic structure, but it doesn't in programming. And one of the nice things about this project is that it forced me to actually acknowledge that. And what do I mean? Well, if I add int max to int max, I don't get an int. Or at least I don't get the reasonable int that I should expect. right? Either we wrap around and overflow or we crash. But neither of those is the right answer. And more importantly, if I start to think, well, int max plus int max equals, the result of that minus int max should equal int max, but like even that's not guaranteed, right? Like weird things can happen when you start to overflow and then sort of go back the other way. Like, do you wrap around the, anyway, point is doing all of this and then trying to run some tests on things that I thought were really obvious, right? I was like, oh, I'm gonna run int, int and addition. That should work exactly like addition in math. No, and float is so much worse. Floating point math on computers is full of sadness, and wow. I mean, it's just sad. I mean, it's amazing for what it is, but it's sad as well. So division and very big numbers, basically very, very large numbers and very, very small numbers become just terrible. And when you start to try to talk about properties and inverses and division and and multiplication, you realize that certain math falls apart. Math breaks when you get to like really, really big numbers. So that's why, honestly, this slide and this understanding is why I did it all. And hopefully it's why you care and why you might do something like this. But largely, that's kind of it. Okay.
So let's see if everybody is still here with all this math. Somebody has to make our brain hurt at one time.
If floating point mathematics is broken or not functional, why did Apple call standard Apple numeric environment sane?
Well, it is fairly sane, right? So, the other part of why I did this is after doing this, I realized that we need a big num, right? Like an arbitrarily sized int. And once we implement that, we'll also be able to get an arbitrarily precise float, right? And even us outside of that, the numeric, the protocols, and all of that are actually pretty well done in terms of enabling the creation of big num and all of those things. And they do what the IEEE spec says. They don't surprise you in that regard. So they are sane. It's just relatively sane.
Just the abbreviation of standard Apple numeric environment. And I wondered why they choose this word as an acronym. Okay,
yes.
I agree. Yeah.
Yes.
All right, other questions? In the meantime, I found it pretty interesting that you said that you didn't have math at school and kind of regretted it. You're the opposite as I am. It was always like, no, not math again. Which, by the way, I had to smile a little bit when you started to talk, because one of the first things that I tell to young people that want to start with computer science, and that's tell me, but I'm not good at math. I tell them, me neither. But so it means it's better if you're good at math to be a computer guy, but it's okay if you are not.
Yeah.
You can survive not being, I would say, excited with math the way you are.
Yeah, and when people say that they're not good at math, I feel like that usually has much more to do with what how math was presented to them and what is expected of them to be a good mathematician. Math is much more about patterns and sort of relationships between things, which I think that this SwiftCheck and this whole experiment highlights, right? Because you don't at no point was I like 3 + 7 is give me the answer, right? It's, well, given two random things, when you put them together, does it matter what order you put them together in? So I think if people were presented with that as math much more early, they would have less inclination to say, I'm not good at it. Because that's what you get when you start to program, right? When you start to program, you're told you're basically describing all of those relationships. You're, you find out whether or not the order that you pass into parameters matters. And so you have to look for those patterns. And you start to, yell at your colleague, like, no, you can't pass them in that order because it matters.
I mean, the sad thing is we are in a two-step process where you learn stuff, like a bunch of mathematical stuff when you're a young child or even later, and then you don't get to apply them. But like 10 years later, you're writing an app and you're like, oh, what was it again with those vectors? And so you have to actually apply it, but by the time you have to apply it, you have to relearn it. So that's the problem, you know what I mean?
Yeah. I mean, I think it would be nice if we would show applications of things like trig in computer graphics or linear algebra in computer graphics and a lot of math in computer graphics. Like a very funny moment that occurred, because I didn't do math at university level, but I knew that I wasn't going to be doing math necessarily at university level, so I tried to get as much in as I could in high school. And so there were definitely some moments before I got serious about math again where I was like, okay, so I'm drawing a circle and I want the line off the circle to come off there. And I'm like, that's a tangent line, cool. So then I looked up tangent line and then I'm, doing trig. And trig was one of the only topics in math that I was like, I guess I'll listen, but when am I going to use this? Yeah. Right? And then, so in the middle of drawing a tangent, like drawing a teardrop shape, I was like, wait a second, I'm using trigonometry right now. This is amazing.
I mean, it's a good candidate for telling how important it is that we finally teach computer sciences at school way earlier. Like all those kids that are learning trigonometry, they could make a pretty simple app. You tell them the 2 concepts and a half of having a view controller and UI kit, and that's it. The rest is math.
So what we really need to do is make it to the point where, like, because it's easy to say a really simple app, but none of our very few of our computer languages actually make it that simple, right? Because it's like, all right, well, we want you to do this programming thing so that you can talk about this math idea. Well, we need the programming to be simple enough that it doesn't get in the way of talking about the math thing, right? And that's just not true a lot of the time right now.
Yeah, although if you think about playgrounds, there's a lot of stuff that you can do in a playground on the iPad where you would just like create a view in a very simple, so you don't have to have the whole boilerplate, blah, blah, blah.
I have an opinion or two about playgrounds. Playgrounds are lovely. Yeah. They're wonderful. But especially the playgrounds that Apple ships right now, there's a lot of magic hidden in ways that can be conducive to what I was talking about, right? Like if you hide a bunch of code in the background of a playground and then say, well, students, you can just type in this and then that, and you can see the results. And that's cool. But I think that right now we have to figure out what we want playgrounds to be for. Are we making playgrounds to teach concepts outside of programming? And if so, what we have right now can work really well, right? Or are we trying to make playgrounds for programming, in which case hiding that much stuff actually makes it harder to figure out what relationship what I typed has to what showed up.
Mm-hmm. Actually, I was thinking about like a blank playground, not a playground book, because playground books are exactly a little bit like you say, a lot of code. Like take this 3D scene kit guy character working around. Obviously, kids don't realize the whole work that it takes to have this scene kit think. Yeah. But if you take like a blank playground and you just teach people like, okay, here's a CG point, here's a UI view, and make something out of it.
See, but then we get back to my original point, which is now you have to teach someone what a CG point is and a UI view, and you spend that time, and then you're like, okay, now that you've got that, now we're talking about trigonometry.
Yeah. Yeah.
Right. So once we can get that first part sort of basically to just disappear when we don't care about it, right? Because if I'm trying to teach you how to draw a triangle and how that relates to graphics, you need to know a little bit about what's going on with the graphics, but really what I want to teach you is the math. Mm-hmm. And just finding the right environment for that is hard right now.
Mm. All right, anyone else has a question? All right. I was going to say you stumped the experts. All right.
They're tired. They're tired. You know, it's a lot of thinking to do in the morning.
Thank you. Thanks for the talk. Just out of curiosity, could you point to a specific example of you wanting to know whether a certain property holds for a given data structure you encountered? Just something specific to chew on?
So concatenation of two arrays is not associative, right? So, you know, that's a weird one to talk about, like not associative, but that's an important thing to think of. You can't, like appending in this order is not the same as appending in this order. But then music theory, like musical intervals, right? So if I have a perfect fifth and a perfect fourth, adding them together in whatever order is associative, right? Like it doesn't matter what order you do it in. Or transposing something is commutative. If I transpose one part of a score and then the other part of the score using the same transposition, should be the same as transposing the whole thing.
Cool, thank you.
I'm the mic mover. It's part of my job is work around with the mic.
So thanks for the nice talk. And are you using this only for music? Well, like you were talking about a lot of music intervals. I did also some generative music and stuff. Do you also use it for generating music, or only for building theory, or trying to make more abstract intervals, or what kind of stuff are you applying it on musical way?
Okay, so I'm not well, I think the question that you have applies just generally, like what am I doing with music theory in terms of code? And an end goal is generating music, right? I am much closer to that than I have been for a while, because I basically spent 8 or 9 years just wandering around and parsing strings and, you know, doing a whole bunch of stuff. But the original goal was, yes, to generate music. Right now I'm worried about voice leading. So once I solve that, then, you know, I'll do a little bit more. If you look at my app in the App Store, chordal text, you type in the name of a chord, or you can basically describe a chord and I can play the music. So I'm generating a little bit of music right now, but I wanted chord or voice leading so that if you play 2 chords, it should smoothly go, you know, as though a pianist was playing, you know, between those 2 chords. And yeah, the end goal is to be able to say, oh, well, I'll generate a score and then I'll make accompaniment for it that'll sound pretty good and that sort of thing.
That's good.
Yeah.
So you talked about integer not being a ring in Swift. Are you aware of a programming language where this is actually the case, in theory, of course, because
yeah, so any language that has big num, right? So like any language that has an arbitrary sized int, like I'm pretty sure Haskell will just grow the size of an int, so it'll be like, oh, well, we can't represent that in 64 bits, so 128, or, you know, however many we need. That has performance implications, sure, which is why most languages are like, you should just tell me when you need that. You know, I know that there's a good implementation of arbitrary sized ints in Scala, for instance. And when you have it, you can talk about the algebraic properties of like integers as though they were the math construct. But when you're not, you can't.
Yeah. Thanks.
All right. I think that's it, right? Nobody else?
All right.
All right. Thank you very much. Let's give TJ another round of applause, please.